Welcome to this explainer. Okay, let's just dive straight into this because we have a lot of crucial ground to cover today. If you are sitting the Cambridge Computer Science or Information Technology exams, and I'm talking about syllabus codes 0417, 0478, 2210, 9618, or the big one, the AS and A-level 9626, you are essentially sitting at an incredibly high-stakes table. Think of it exactly like Casino Royale. The examiner? Well, they're the dealer. And understanding their exact mindset is your ultimate cheat code to winning this game. Because here's the truth. You don't just need raw textbook knowledge anymore. You need to know when to hold, when to fold, and exactly when to go all in on your answers to extract every single mark. Today, we are completely decoding one specific, notoriously tricky area of the syllabus. Topic 3.2. This covers electromagnetic field sensors, ultrasonic sensors, and induction loops. We are going to completely transform your approach from standard memorization so you can play the examiner's game and win big.
Literally, the principal examiners are telling us this directly in their reports. They say, and I quote, "The difference between a B and an A star in information technology often comes down to how well you understand 3.2 electromagnetic field sensors, ultrasonic sensors, induction loops." Now, you might be wondering why this specific topic, because this isn't just another chapter to lazily skim through on a Sunday afternoon. This is the absolute battleground where top grades are decided. It requires laser precision, deep critical thinking, and knowing exactly how to format your responses for maximum impact. If you can master this, you can master any complex topic they throw at you.
So here is our masterclass blueprint for today. We'll start by decoding the examiner's mindset, then move into sensor theory fundamentals, break down the method mark strategy, jump into a highly interactive critical analysis workshop, and finally reveal the top examiner warnings.
All right, Act 1, decoding the examiner's mindset. Let's look at the absolute rules of the game.
Look, in the Cambridge IT and computer science exams, just vomiting facts onto the page is not going to cut it. It simply won't work. The syllabus targets distinct cognitive domains. Sure, they want knowledge and understanding, but they massively test application and analysis. Consider this actual past paper question we see here on induction loops. Let's look at two typical students. First, we have Alex. Now, Alex overloads the page with raw facts about electromagnetic fields, writing paragraphs of physics theory, but provides absolutely zero context. There is no application to the scenario actually given in the prompt. The result? A total loss of marks, red ink everywhere. Meanwhile, we have Sam. Sam looks at the clock, panics, rushes the answer, and completely ignores the evaluate command word, choosing instead to just describe what a sensor is. Because Sam missed those vital command word requirements, the assessment objectives are totally missed. To get the highest marks, you have to decode the command word first, and then anchor your brilliant technical facts directly to the specific context. Moving on to Act 2, Sensor Theory Fundamentals. It's time to build a theoretical architecture that won't collapse under pressure. The principal examiner reports consistently highlight a really crucial pattern. Top-performing students don't just memorize dictionary definitions, they understand causal relationships, and they integrate this topic with other areas of the syllabus. Furthermore, the reports show that candidates constantly confuse key terminology. Listen to me on this, you must always define your technical terms before using them in extended responses. It is a non-negotiable first step. If the question involves an ultrasonic sensor, start by defining it clearly as a device that measures distance by emitting high-frequency sound waves and calculating the time it takes for the echoes to return. Establishing that precise definition proves to the examiner immediately that you know your core principles, setting the tone for a high-scoring answer.
So, how exactly do you structure this knowledge when writing? The answer is the Peel framework. Point, evidence, explanation, link. This is the core strategy for structuring your IT and computer science answers to ensure you hit every single cognitive domain the examiner is desperately looking for. Now, before we break down exactly how to use this framework to guarantee those top marks, I need you to do something. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to the strategy.
All right, it is time for a 30-second challenge. I want you to look at the text and spot which sentence represents the point, which is the evidence, which is the explanation, and which is the link. Ready? Let's say a question asks about the limitations of an induction loop at a busy city traffic light. Your point is your initial, bold claim. Your evidence is the hard technical reality, like the specific magnetic field properties required. The explanation is where you show off. You detail exactly why that matters, such as the risk of electromagnetic interference from other nearby metal objects or power lines. And finally, the link ties it right back to the specific context of traffic flow mentioned in the prompt. If your answer has those 4 distinct structural pillars, you are practically forcing the examiner to give you maximum marks.
Act 3, the method mark strategy. This is where we learn how to get marks for the process, not just the final destination.
In Cambridge IT, especially when dealing with complex topics like sensor data processing, marks are heavily awarded for the actual process. If you just jump straight to the end conclusion in your head and write it down, you lose out massively. The syllabus actually outlines a standardized procedural framework. You need to follow these 5 steps to guarantee those vital method marks. Step 1, identify the key elements from the text or the data tables. Step 2, apply the relevant theoretical principles to those elements. Step 3, execute your analysis with clear, visible working. Show them how you are thinking. Step 4, verify your results to check for logical reasonableness. And Step 5, present the information in the appropriate format, using proper headings and clear professional annotation. It is a systematic, highly repeatable process that works every single time.
Let's actually watch this transformation happen live on screen. Compare this vague B-grade answer, which casually states that ultrasonic sensors bounce sound off walls to tell you when to stop. It's kind of true, but it's weak. Now look at the A-star grade answer. This one identifies key elements and applies principles by detailing high-frequency sound wave reflection and explicit time-of-flight calculations. The top-tier answer executes an analysis of environmental factors that might affect the speed of sound, and it presents all of this with strict, correct terminology. This takes all those red pen marks and turns them into beautiful green check marks by being highly specific and demonstrating cross-topic connections. That is the gold standard.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Seriously, do not leave your grade to chance. Let's get back to the breakdown.
Welcome to Act 4, the Critical Analysis Workshop. Get ready to actively scan and evaluate.
In the real exam, you're going to be presented with incredibly dense texts and complex tables, and you have to extract relationships and draw solid evidence-based conclusions. Here is challenge 1, the data scan. On screen, we have a complex data table showing various electromagnetic and ultrasonic sensor readings across different extreme conditions, things like heavy rain, dense dust storms, and massive temperature fluctuations. I'm putting a visual 60-second countdown in your mind right now. Your job is to rapidly extract the core trend. For instance, what exactly happens to the ultrasonic sensor accuracy when the ambient temperature drops drastically? You need to quickly identify that relationship. Since sound travels slower in colder air, the time of flight calculation changes. If you can spot that from the raw data under pressure, you are golden.
This leads us to a crucial question. Why do students find applying concepts to unfamiliar contexts so incredibly hard? It's simple. They panic. They see a scenario they didn't specifically study in their textbook, and their mind goes blank. The ultimate solution to this is the deconstruct, solve, evaluate problem-solving method. You deconstruct the terrifying new information, break it down into logical, manageable steps, solve it systematically using your core theory, and then evaluate your evidence. Top-scoring candidates constantly demonstrate this evaluative thinking by questioning the underlying assumptions of the scenario.
And that brings us perfectly into comparative analysis. When an examiner asks you to compare, let's say an electromagnetic field sensor with an ultrasonic sensor, they absolutely demand evidence-based comparisons. You cannot, under any circumstances, just list the features of one and then list the features of the other in a separate paragraph. That's a trap. You must use comparative connectives like whereas, conversely, or similarly. You must highlight both similarities and differences in the same breath. And critically, you have to evaluate limitations, assumptions, and alternative interpretations. What are the limitations of an ultrasonic sensor in a vacuum versus an electromagnetic one? Well, sound needs a medium to travel, electromagnetic waves don't. You have to weigh these facts directly against each other to unlock the analysis marks.
Let's test everything you've learned under pressure with Challenge 3, speed writing. You have 30 seconds to draft one perfect paragraph on induction loops, applying the Peel method to a totally unfamiliar context. Let's use an automated smart parking garage. Point: state the sensor's function clearly. Evidence: mention the specific magnetic field disruption caused by the metal chassis of a car entering the space. Explanation:
detail exactly how this analog data is converted and processed by the central garage system. Link, connect it directly to the overall efficiency and traffic flow of the parking garage. If you can mentally draft that structure in your head in 30 seconds, you are genuinely ready for whatever they throw at you.
We have reached Act 5, the top examiner warnings and your final success blueprint.
We've looked at everything you should do, but what are the deadly traps that consistently cost students their A-star? Here are the top 3 mistakes pulled directly from the principal examiner reports. Mistake number 1, answers are way too vague. As we've seen, examiners crave specific technical detail. Don't say it sends a signal, say it transmits a continuous electromagnetic field. Mistake number 2, forgetting to check format and presentation. Strict conventions actually matter in IT. Use proper headings, clear annotations, and logical paragraph breaks. Mistake number 3, answers are not specific to the context given. If the question is about a self-driving car's sensors, do not give a generic answer about a factory conveyor belt. Anchor your knowledge tightly to the prompt you are given.
To help you avoid these mistakes when the exam hall pressure hits, here is a brilliant memory hack for you. Create a custom acronym for your analysis checklist. I highly recommend the acronym LACE: Limitations, Assumptions, Context, Evidence. The minute you sit down and see an evaluate question regarding any sensor system, just scribble LACE in the margin. Then ask yourself, have I discussed the limitations? Have I explored the assumptions made by the system? Is my answer firmly applied to the context? And finally, do I have solid technical evidence? This simple, foolproof trick ensures you literally never miss an evaluation mark again.
Now, let's pull this entire strategy together into your ultimate computer science success blueprint. Remember, exam success is a highly systematic process. It is not just luck. Here are your 3 core rules. 1. Command word decoding. Always identify what the question is actually asking you to do before you write a single word. 2. Peel framework application. Structure your paragraphs perfectly every time. 3. Time management matrix. Allocate your time based strictly on the method marks available, ensuring you have enough time to deconstruct, solve, and evaluate without rushing at the very end.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by without having the best possible strategy in your corner. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Master the examiner's mindset, apply the frameworks we discussed today, and go walk into that exam hall like you own the place. You've got this.